Alright, now we're going to start with our chapter 2. So in chapter 2, we're going to learn about motion. We're going to learn about a lot of new formulas that you have already learned during your Form 1, Form 2, Form 3 studies. But we're going to go much deeper to those topics and we're going to apply it in different equation as well. So in chapter 2, we're going to start with linear motion. Now, in physics, we have two different kind of motion. The first one is a linear motion where everything moves on a straight line. And then we're going to learn about centripetal motion. This involves celestial bodies such as planets, moons, the stars, how it moves along an orbit, and that is for chapter 3. So we are going to focus on chapter 2 first. So in a linear motion, it involves the movement of an object from point A to point B. This motion from point A to point B, this is the length. And within length, we have two different units. The first is distance, and the second is displacement. The difference between these two is that they are separated by either they are a scalar quantities or a vector quantity. So we're gonna shift from here to something else first. So we're gonna talk about scalar quantities and vector quantities. In scalar quantities, we only use quantity that have magnitude only. In vector quantities, they have both magnitude and direction. For example, let's say I have an object and this object travel 100 meter. So if I were to say it's a scalar quantity, where it only contains the magnitude, the box move 100 meter. So this 100 meter can either be to the front, to the right, to the left, or to the back. That's why this statement is a scalar quantity. It doesn't have any direction. And then we go with a vector quantity. The box move 100 meter to the east. So because it's moving to the right, so we said that the box move 100 meter to the east. So this movement have its own magnitude as well as direction. Alright, next we shift back here. So we start with distance and displacement. In distance, this is a scalar quantity or a scalar unit, and a displacement is a vector quantity or vector unit. So both distance and displacement, they are measured in meter. And for both of them, their symbol is still S. Now, in linear motion, we go with the distance and displacement. We go one by one. So if I were to say this ball moved from point A to point B, let's say I'm giving you a simple map. Let's say here is Abu's house. He go to Chong's house. Then he go to the library. Then he go to school. Now, from his house to Chong's house, let's say this is 80 meter. From Chong's house to library, let's say this is 100 meter. And from library to school, it's 30 meter. Right? So what happened here? If we are talking about distance, distance is measured in this manner. So the distance would be 80 plus 100 plus 30. So your total distance would be 210 meter. Now, that is for distance. For displacement, because displacement only involves the vector quantity, displacement can be said a shortcut between where you come from to the point that you arrive in. So for this case, Abu's displacement would be described as this length. It's a straight line connecting between his house and the school. So we can create a triangle, and we can take out this triangle on this side. So we know that the horizontal distance is 100 meter. We know that the vertical distance is 80 minus 30, we're going to get 50. Now, to get this point, the displacement would be a square root of 100 square plus 50 square. So you're going to get a square root of 12500. So when you calculate, you're going to get your displacement. Here is the unit meter. So I'm just going to leave my answer inside. So the distance and displacement difference is that for distance is the exact path. Each path that you take, you include in your calculation, and total up, you're going to get your distance. For displacement, it is the straight path from one point to the next point. And of course, for displacement, we're going to have a direction. So here, the direction, usually we try to find the angle here, which is equivalent to this angle right here, and we can use tangent for this. So tangent theta equals to opposite over adjacent. So you can find your theta by pressing your calculator, and you're going to get your answer. Now, I'm going to shift back here. Not going to dwell here for too long. We're going to go with the other components inside our linear motion. We have speed, and velocity. So both of these are basically using up the thing on top of it. So speed is a scalar quantity and velocity is a vector quantity. So for speed, since it is a scalar quantity, the value is always positive regardless you're going forward or you're going backward. For velocity, if you're going forward or you're going to the right, it's always positive. You're going backward and to the left, it's always going to remain as negative. So for speed, since it's a scalar quantity, always positive. For velocity, it can be either positive or negative depending on direction. But both of them share the same formula. To get speed, the symbol for speed is V. It's equals to S over T, where for speed, it's distance over time. For velocity, it is displacement over time. So for this, the unit for speed is always m as -1. Now, from speed and velocity, we have another thing that we can calculate, which is the acceleration. I'm going to talk about velocity and speed later. I'm just going to focus on acceleration because we're going to learn about the 4 formulas of motion. So for acceleration, the symbol is A. So acceleration, regardless you're using for speed or velocity, it doesn't matter. So for acceleration, A equals to V minus U over T, where V is your final velocity, your U is your initial velocity, and the unit obtained from acceleration is always ms negative 2. Where does this 2 come from is because the first unit of time exists from your velocity and your speed. The second unit of time comes from the formula itself. So here for linear motion, there are 5 things that you need to be aware of: the distance, the displacement, the formula of speed, the formula of velocity, which is the same thing, and then lastly we have our acceleration. Alright, and then we're going to continue next on to the formula of motion. Done. Right, now we're going to talk about how the graph and how do we calculate from the graph. This is something that you already learned in Form 2 mathematics, and we're going to use what you've learned in mathematics and going to apply it to our physics. So in physics, for linear motion, we have graphs that affect a motion where we can calculate the components. So we have 3 graphs. The first graph is the displacement time graph. So on the y-axis is displacement, on the x-axis is our time. Next, we have our velocity or speed time graph. The y-axis is velocity or speed, and the x-axis is time. And finally, we have our acceleration time graph. Y-axis is our acceleration and the x-axis is time. Now, what happened here is that for So what happened here for our displacement time graph? So we have a graph of something like this. So if it is distance, there is nothing underneath the x-axis. If it is distance, there's nothing underneath the x-axis. However, if it is a displacement time graph, the negative of our y-axis beneath the x-axis or beneath the time axis, it's where our motion is moving backwards. We're going to talk about this later. So what happened here? Let's say the motion is something like this. So here we have several things that we can explain. The first thing is that this is where our motion is happening, where velocity is constant. Here the object is at rest. Here constant. Here at rest. And if it is turning back, this is returning to position. Remember, this is as distance or displacement. So what happened here? Here, the gradient from here, our gradient will give us either speed or velocity. So for a displacement times graph, we're going to get a velocity, and anything underneath our x-axis is basically, this is for the displacement time, the motion to the left. So if I were to explain it in terms of ball, let's say I have a ball. This ball is moving to the right. It stopped. It's not moving for several times. And then it moved further to the right. It stopped. And it returned back to original position. And the remaining graph is where the ball moved to the left. And this only happened for displacement time graph. For distance time graph, if the ball keep on moving to the left, the graph here will just stay on the upper side of the x-axis, upper side of our time axis. Alright, so this is how the motion is for this graph. Now, area under the graph for displacement time graph or distance time graph won't give you anything. But when we look at velocity time graph or speed time graph, Now, here we have several things. So the first thing, this is what we call a increasing velocity, or we can say that this is a constant acceleration. Here is where constant velocity happens. Similarly, here is increasing velocity. Now, on this side, it can mean two things. The first one is either this object is down stopping, or we can say that it's undergoing deceleration. And anything underneath means that it's reversing its motion. So it's moving to a stop here, and then it reverses itself. So anything underneath this is a reverse motion. So for velocity time graph, your m value, your gradient, will always give you acceleration. The area underneath a graph of velocity time graph will give you your distance or displacement. And lastly, we're going to take a look at acceleration time graph. For acceleration time graph, they do not have any gradient. So it's either something like this, or something like this. It looks like a stair. So when the value of A is positive, here we have acceleration. So acceleration is positive. Here acceleration is 0. And the last one, we have deceleration. So in other words, your A is a negative value. Now, since this graph doesn't have any gradient, the only thing that you can calculate from here is the area, where the area is equals to the velocity of the object. Now, these three are the common graph that you will see in your physics question. However, there are certain other graphs that might seem a bit peculiar when they are used in this manner. So, for example, let's say for displacement or distance time graph, you have something like this. So, this is the motion of an object that is accelerating. Okay, so what happened here? This speed of the object keep on changing as it moves against time. And then if let's say your graph is something like this. So here, this is decelerating over time. Now, the same thing happening here. So here, let's say you have a graph that is shaped in this manner. Now, here it's accelerating, means that the A is constant, it's not changing. Here, the acceleration change. So we can say that acceleration increases. So in other words, when an object is moving in this manner, producing this graph, means that the velocity is not changing, it's not shifting constantly, it just jumps very high. For example, at the first second, the speed is 10 meter per second, second it go to 35 meter per second, third second, it jump to 80 meter per second. So what happened here, you have an increasing acceleration. So if you're driving a car, you are slamming on the accelerator where the speed of the car shifts drastically. So this is the graph, the shape of your graph. And finally, if your graph is something like this, this is what we call decreasing acceleration. Now, just a mental note, for acceleration time graph, the acceleration of an object does not, if it is 0, it does not imply that the object is at rest, because acceleration only involves velocity. If your object is at rest, your acceleration is actually non-existent. And we're going to continue next to free-falling object. Right, so earlier we already learned about how we use the 4 linear motion formula to solve our problem. Now we're going to go with how it is applied, or how we are conducting it in the form of experimentation to prove that linear motion exists. So for this topic, we're going to focus on the usage of trolley, a ticker timer, and a ticker tape. So in this experiment, we use wooden block